Hi everyone, this is Professor H. Rahman from Agricultural and Food Engineering Department, IIT Kharagpur. I welcome you to this NPTEL online certification course on traction engineering. This is lecture 16 where I'll try to cover tractive effort and sleep for a truck. The concepts covered will be again sleep as well as tractive effort. As we know, a truck has a bigger contact area. If you look at the figure which is shown in this slide, it has a bigger contact area. So the maximum tractive force which is developed is denoted by F max, which is equal to shear stress, maximum shear stress into area. Now, when I say tractive effort developed, that means it is a component of shear stress, shear force which is developed at the contact patch, and shear force is nothing but the shear stress which is developed. And if you know this relationship between shear stress and shear displacement, then knowing the displacement, you can find out what is the shear stress which is developed, and knowing the contact area and shear stress, you can calculate what is the shear force which is developed in the contact patch. Now, the equation which is given here is the maximum thrust which is or tractive effort which is developed, which will be equal to contact area A into shear stress tau max. So, in other words, I can write as A into C plus W tan phi. So, where A is the contact area, C is the cohesion, and W is the weight acting on the truck, and phi is the angle of internal friction. So, if you look at this equation, when a truck is operated in sandy soil, pure sandy soil, there is no cohesion. So, area has no role. It is the W which plays, or it is the weight which plays the most of the things. That means it controls the maximum thrust which is developed. Now, if it is a clay soil, then area comes into picture and W has no role. But the equation cannot be applied for all conditions. It is only giving you maximum thrust. If you are or anybody is interested to find what is the thrust developed along the contact patch, then we have to know what is the shear displacement under the truck at the interface between soil and truck. So, to predict the relationship between thrust with tractive sleep or truck sleep, we have to examine the development of shear displacement beneath the truck. So, it is very simple in the sense, because shear stress is a function of shear displacement. So, you have to find out what is the shear displacement at the contact patch. If you look at the figure, there you can see I have indicated 1, 2, 3, 4, 5 points. One is just at the beginning, because this truck is moving in a direction which is given by this arrow, and this is the powered wheel which is driving, and these are the rollers for giving tension at point 1, point 2, point 3, point 4 and point 5. Point 5 is the end point, point 1 is the beginning of shearing. Now, the shear displacement which is developed at point 1 and the shear displacement which is developed in subsequent points, they are not same. Why it is so? Why there is a variation in this shear displacement? Because the link which is shearing at point 1 is just coming in contact with the soil, whereas the link which is present, link means link in the truck, which is present at point 2 and present at point 3 or present at point 4, they are shearing the soil for a considerable period of time. That's why shear displacement is more as you move towards the rear end of the truck. That means this is the first point is the beginning point, last point 5 is the rear end, front end, rear end. So, as you move towards the rear end, your shear displacement is increasing, which is indicated in this figure. and it reaches a maximum value, because after that there is no contact. Again the track will be, the links will be not in touch with the soil. So when the moment it leaves the soil, it comes to this position, and there is no shear displacement developed by this link. Okay. So the maximum which is developed is at this point at the rear end, and the minimum which is developed is at the front end. Now, how to find out the shear displacement? So again, we know what is the slip velocity. What is the slip velocity which is present? The slip, which can be defined as I is equal to 1 minus V by omega r. Omega r is the angular speed of the sprocket, and r is the radius of that sprocket which is driving. So omega r will give you virtually the theoretical speed, which is denoted as Bt. So I can write as I is equal to 1 minus V by omega r is equal to 1 minus V by Bt. And if I simplify this one, then Vt minus B by Bt. So V is the actual velocity, and the difference between theoretical speed and actual speed is denoted as Bj. So I can be written as Vj by Bt, where I is the slip of the track, and omega is the angular speed, V is the actual velocity of the track, Vt is the theoretical speed of the track, and Bj is the speed of slip of the track. Now suppose I am interested in finding out shear displacement at a point which is at a distance x from the front end of the contact area. So before that, let us know what is the slip velocity, Vj. Vj, when it is acting opposite to the direction of motion, that means the track is slipping. When it is acting along the direction of motion, then the track is skidding. So I have indicated here Vj direction, indicated here the track movement. So these are in opposite direction, so the track slips. Now Vj doesn't vary along the track length, since link cannot stretch, so or the track cannot stretch. So that's why we assume that Vj is not varying, it is constant. So slip velocity is constant below the track, and Vj is opposite to the direction of travel. Now if you are interested in finding out shear displacement at a distance x from the front end of the contact area, so this is the point, say A, now which is at a distance x, then x will be equal to Bj into t. Bj is the slip velocity, t is the time, that is the contact time. So now t will be equal to, if t will be equal to, if Vt is the theoretical speed, then time will be equal to x by Vt. Now if you substitute this expression in this equation, then J, that is shear displacement, will be equal to Bj into x by Bt. So that is equal to Bj by Vt. We have already expressed that this is equal to the slip. So instead of Bj by Bt, I have written I. So J will be equal to I into x, which indicates that shear displacement is a function of slip. Shear displacement is a function of distance or the point under consideration. What is the distance from it, what is the distance of this point from the front end? So if you look at this equation again, then what you can observe is that the shear displacement is linearly varying with I. Okay, it is varying from front to the rear end of the contact area linearly, and with increase in slip, its value is increasing, and that's what is reflected in this figure. or 10% sleep, 30% sleep, 50% sleep, 70% sleep, 100% sleep. So how this displacement is varying. So J is on the y-axis. Okay. So this figure shows that shear displacement is a function of sleep, it is a function of distance. Now suppose I increase this distance to this point. So this is the point B. So now this will be the displacement. If I draw a vertical line, this will be the shear displacement. So next question is, what will do with this shear displacement? Once you calculate shear displacement, what next? So next is to find out what is the relationship between shear stress and shear displacement which is existing. So in nature, what we observe, there are three categories of relationship available. One is for loose sand, saturated clay, and most of the disturbed soils, and the other one is for organic terrain, and the third one is for compact sand, silt, and loam. So you can take either of these equations which can be utilized to find out what is the relationship between shear stress and shear displacement. So once you finalize this, then we have to find out what is the shear thrust force developed. Suppose, for example, we try to find out, we try to take the relationship that is in loose sand or saturated clay, where relationship tau is equal to tau max into 1 minus j upon k. So tau max I have written as C plus sigma tan phi into 1 minus e to the power minus j upon k. So here sigma we have considered as the normal stress which is acting on the track, and that is uniform along the track. It is not changing. So if that is the case, then thrust force will be equal to, how do you find out thrust force? Once you know the relationship for tau, so we try to plot tau versus the displacement. Then at 10% sleep, this will be the curve, and at 50% this will be the curve. So like that you will get a series of curves by varying the sleep. Now if you want to find out thrust force, then you have to find out the area under this curve. So area under this curve means you have to multiply shear stress with the area. So what I have done is, F will be equal to tau b into dx into tau. So that has to be integrated along the length. Suppose the contact length is L, so 0 to L. So that's what is written here. Now if I integrate it by putting the relationship between tau and tau max, then this is the relationship which you have taken. So this has to be integrated now. So what finally you will be getting is, if you integrate, so you will get an expression for thrust force for a loose soil. Okay. For a loose soil, what will be the thrust force? Okay. Now the final expression for this will be, F will be equal to B into C plus, and P I can write as W. Since we have assumed P is equal to W by BL, assuming that the pressure is constant beneath the track. So W is the weight, B is the width of the track, L is the length of the track. So W by BL will give you what is the contact pressure. So instead of P, I can write W by BL. So C plus W by BL tan phi, then L minus K by I into 1 minus e to the power minus I L by K. Okay. Now if I take L common out, then it will be CBL plus W tan phi into 1 minus K by IL into 1 minus e to the power minus IL upon K. This will be the final expression for thrust. Now if you know the rolling resistance, then you can find out what will be the pool developed. So pool will be equal to thrust minus rolling resistance. So, and if you want to find out the tractive efficiency, then pull by weight will give you the tractive efficiency. Pull by weight into 1 minus S. So, tractive efficiency eta will be equal to coefficient of traction. This is nothing but P by W into 1 minus S divided by COT plus CRR. COT is P by W and COT is P by W and CRR is RR by W, motion resistance by weight. Now, if you look at this equation, it is the length that controls the thrust force. If you have same contact area, one is having a higher length, lesser width, the other one is having a wider width, lesser length, then it is the length of the track which controls the thrust force. More the length, more will be the thrust force developed. So, in design you have to keep this in mind. Whenever you got some area, try to keep more length so that you will get more thrust force developed. And since length is more and contact area will be same for both the cases, so rolling resistance will be nearly same. Only the thrust force will be more, so that's why the ultimate pull will be higher in case of lengthy track. Next is we are talking about the distribution. Here very nicely we have assumed that the pressure is uniform, so we have taken W by BL. If pressure is not uniform, what are the other possibilities? So let us now discuss those possibilities. So there are 1, 2, 3, 4, 5 kinds of pressure distribution. One is uniform pressure distribution, where I have indicated P is equal to W by BL, and if that is the case, then this is the thrust force developed. Now in the other case, there will be sinusoidal kind of things. Now you are getting some peaks at regular intervals. If n is the number of peaks, then P can be the pressure, or the normal stress distribution can be written as W by BL into 1 plus cos. Thrust force will be equal to this one. F is equal to W tan phi into 1 plus K by IL into e raised to the power IL by K minus 1 plus K into e to the power minus IL by K minus 1 divided by IL into 4 n square K square pi square by I square L square. So, it all depends on what is the pressure distribution. Now, similarly, when the pressure distribution is minimum, the 0 at the front end of the track, maximum at the rear end of the track, then P is equal to 2W by BL into X by L. If pressure distribution is maximum at the front end, minimum at the rear end, then P will be equal to 2 into W by BL into L minus X by L. Similarly, if the pressure distribution is gradually changing, reaching to a peak, starting from the front end, and at the rear end it is again coming to 0, then P will be equal to W by BL into pi by 2 sin pi x by L. So, on the right side I have given for all these 5 conditions what will be the expression for tractive force. These are all derived based on that integration, where the pressure distribution is to be substituted by this, and then you have to integrate it, and finally the expression is given here. So, what you conclude from here is thrust which is developed under a track, it depends on what is the pressure distribution, and it depends on what is the shear stress shear displacement relationship. If you can find out this relationship for different conditions, then we can find out what is the thrust developed by integrating along the contact area. And then if you know the shear stress, we will try to find out the shear force by multiplying with the area. So this is how we will try to find out the tractive effort for a truck. So only thing is, one has to know what is the pressure distribution and what is the shear stress shear displacement relationship. Then one can find out what is the thrust which will be developed.